MG is just called the Dirac mass for the neutrino. It preserves lepton number. There are 4 components altogether. And in the, one can define a Dirac field. I should have written this up there. This is the same as M psi bar psi, where psi is equal to psi left plus psi right. You can put these two Miles centers together to make a 4-component Dirac field, and then the mass takes the simple form. This is sort of backwards from the way I did it before. Before I introduced the Dirac field and projected out left and right. Here I'm studying with independent left and right and putting them together to make a Dirac. Okay. So I can do that for a neutrino. And we have 4-component nu left plus nu right. We have 4-component L conserved. Delta T3 left is equal to plus or minus a half. That is, this is active with T3 of a half. This is sterile with T3 of 0, etc. So we really have to generate this. We really need to have X come in. So it would be nu right, nu left. And so we're violating with isospin by 1/2 unit. So you can't have a bare mass term. It has to be generated spontaneously by Higgs mechanism, just like all the other fermion masses in the standard model. Now this is perfectly fine. The only problem is that the MD is what I call H nu, and this is just the Yukawa coupling that sits here. And it's actually a root 2, and then there's a nu over root 2 here. And this is H nu times 246 GeV, and the whole thing is less than about 1 electron volt experimentally, so you have to have H nu less than about 10 to the minus 11. Yes. Nu has is used twice in these equations. This is neutrino, this is the weak interaction state. Yeah. It's just, I always talked about this matrix gamma, which was, mass matrix I always showed it some gamma times nu over root 2, and so I'm just calling the gamma would be H over root 2 is all. And I got eigenvalue. H is just one of the eigenvalues of gamma over root 2. The root 2s are such a nuisance. There's, I can make the same in any context. I have tried and have other people to find a test notation, but the root 2s, etc., are such that if you make one equation look simple, another equation will always look awkward. Yes? The right-handed neutrino is still okay. It's a sterile, yeah. It's the one I was introducing in the SU2-1 model. And you can generate a mass this way. The only problem is many people feel that it is unaesthetic or unsatisfactory or fine-tuned to have a parameter that is less than 10 to the minus 11. Now, once you contrast this, the corresponding parameter for the top quark is of order 1, and the corresponding parameter for the electron is of order 10 to the minus 6. So the electron Yukawa is pretty small too. It's still 10 to the minus 11 is a lot smaller than 10 to the minus 6. So the simplest way to generate a Dirac mass is just by elementary Higgs mechanism by fine-tuning. Most detailed models actually impose some extra symmetry on the standard model. It might be a bigger gauge symmetry, it might be a global symmetry, it might be a discrete symmetry, but most models impose some extra symmetry that forces H nu to be 0, the first approximation, and then some perturbation around 0, a very small value. So it is possible, or by fine-tuning. However, there's another possibility, and this will be the last thing today, Majorana mass. I can be more economical by using the right-handed field up there that I already have, namely the nu c right. This would be for the neutrino MC over 2, the 1/2 is sort of like the analog of a 1/2 for a Hermitian scalar. Instead of introducing an independent right-handed biofield, let's just make use of the CT conjugate of the one we already have. And this will be written as MC over 2, nu bar M, nu M. So we call this nu sub T for Dirac. Nu sub M is nu left plus nu T right. Majorana is the name of the physicist who invented this. You've also seen this name in connection with perhaps with a Majorana representation for gamma matrices. And he had an interesting story. He was I guess in the 1930s, he got onto a ferry boat from Sicily to Italy and didn't get off the boat. Disappeared. Never seen again. But anyway, this is more economical. Nu M goes under CP to itself. It's its own CP conjugate. And there are two components. Only new left, new C right, they're both active. L is violated. 2 units. L, the electron number transformation here and here clearly is not a symmetry, it's violated. And in fact, pictorially, you have new C right goes into new left, antineutrino into neutrino. But you know, in a field theory, you can always sort of twist the visor out. You could have just as well, you could have out of nowhere, you could have two new lefts emerge, just like, you know, the incoming antineutrino also corresponds to an outgoing neutrino. So there's delta L equals 2. T equals triplet here. And that's because the delta I3, the delta T3 left is plus or minus 1. You go from minus a half to plus a half. So you're violating weak axis then by a full unit. So Fu2 cross U1 would not allow, would not allow their mass term. And to generate this, there's basically two ways. One is introduce a Higgs triplet. Turns out it has to have a double charge, a single charge, and a zero to get everything right. And then you could generate this term by coupling with this phi 0 if it had a down. Now you need to have H phi 0 less than 1 electron volt. If this guy is comparable to the electroweak scale, you haven't gained anything. It still has to be small. But if somehow this bell is very tiny, then this could be larger. In practice, models like this have not been very successful. There are all kinds of other constraints on such theories, but in principle you could have it. The other possibility here is what we call a higher dimensional operator. Higher dimensional operator. That is to have a engineer some interaction, new C right, new left, coupling to two. These are the ordinary Higgs doublets, new. This is a non-renormalizable interaction. The non-renormalizable interaction is always scaled by some mass parameter. And this would give an MD in Majorana from mu squared over M. If mu is 246 GeV, and whatever generates this, perhaps the exchange of some massive particle mass M, if that's of order 10 to the 14 GeV, then that would give a small mass. This is called a seesaw. The small neutrino mass is inversely proportional to some very large mass scale. And this mass scale may be generated by some underlying string theory or some underlying heavy particle. One particular manifestation of it I'll mention tomorrow is called the type 1 seesaw, which is just a heavy sterile neutrino. So those are the two possibilities. We do not know which is the one chosen by nature. And empirically, either a small direct mass term or a higher dimensional operator sometimes specify what goes on inside this blob to generate the operator. Okay, so I'll finish that story tomorrow and talk about the experimental constraints, and then I'll sort of talk about general perspectives on where the standard model is going or not going. And as I discussed yesterday, there are basically two possibilities. One can introduce, in addition to the so-called active neutrino and its CP partner, the one that has normal territory weak interactions, one can introduce an Fu2 singlet or sterile and its CP partner, and one can put them together to make a normal Dirac type mass term, just like the masses that we have for the charged leptons and quarks. And the only problem with this is that the necessary Yukawa coupling, when you generate this by the Higgs mechanism, has to be extremely small. And many people consider that not very aesthetic, or that should have some better explanation. And such Dirac mass terms involve four components: the new left, new C right, and then the two components of the sterile. They have a conserved lepton number lepton goes to lepton, and they violate with isospin by 1/2 unit, and that's why they have to be generated by some sort of Higgs mechanism. One can also introduce the Majorana-Mass term for the active neutrino, which connects the neutrino to its own CP conjugate. This has only 2 components. It violates lepton number by 2 units because it involves taking a neutrino into an antineutrino. And it also violates weak isospin by 1 because you're going from a T3 of minus 1/2 to a T3 of plus 1/2. So this can be generated by either a Higgs triplet. So this is some phi, which is a Higgs triplet, requiring a valve, or it can be some higher dimensional operator involving 2 Higgs doublets and some coefficient 1 over some large mass scale. And a higher dimensional operator may well be due to some underlying physics inside this blob in much the same way that the full Fermi interaction of the Fermi theory we now know is really due to the exchange of the W. So what I didn't have time to say yesterday is one can also introduce a Majorana-Mass term for a sterile neutrino, taking its right-handed neutrino into a left-handed antineutrino. Here the S actually means singlet, not sterile, but here this means triplet, and this means either doublet or Dirac. And this also has 2 components. Sterile does. It also violates lepton number by 2 units. But since these are pi2 cross U1 singlets, it does not violate weak isospin. So you could actually write this down as a bare mass term in your Lagrange. If you're willing to violate lepton number, which is only a global symmetry in the standard model, you could just write this down as a bare mass. So this would take nu right into nu C left. It could be a bare mass or some nu Higgs singlet. Although it could be a bare mass as far as the standard model is concerned, in most concrete models that implement this idea, it is really some phi S of singlet that generates it. So that's basically where I left off yesterday. Now, are there any questions before I proceed? Yes.
So you're questioning that you stack
Yes, you could say it that way. There's 2 physical degrees of freedom for the active nu left and a CP conjugate. And there's 2 components for a sterile, nu right and a CP conjugate, so each has 2 components. Now, formally, if you start out with a 4-component Dirac spinner, that's got 4 Dirac spinner indices, and these are vial states in which you project out 2 of them, so 2 of them are 0. You can also, if you're just talking about these vial state components, there's actually a 2-component notation for it as well, where the spinner has 2 components. But the main issue is that there's 2 physical degrees of freedom.
Yes, I was thinking about that as well. They're just adding the master to the technical progression.
If I say that this has a lepton number of +1, then it violates a fermion number. It takes a particle into its own antiparticle. Yes, if you want to say it that way, yes. However, when this is used in practice, is one usually says, well, it's assigned the nu left and the nu right to the leptons, and both of them the antiparticles to the anti-leptons. But you're right, you could technically, if you just have the sterile off by itself, completely isolated, no couplings to anything else, then it would make more sense to say what you're saying. Okay, now you can put these together, of course, with 1 sterile and 1 active to make a 2x2 mass matrix, which is of the form nu bar C left, MT, MG, MT, MS. So this is nu C right, plus Hermitian conjugate. So if I introduce both, I could have all of these present simultaneously. If I introduce, 2, an active and a sterile. So NT would be the Majorana-Mass term that couples this to this, plus its Hermitian conjugate. The MS would be the sterile case that connects this to a CT conjugate. And the Dirac term, well, I got 1/2 here, MD, and it's mu bar left, MD, mu C, mu right. And then it's 1/2 of mu bar C left, mu C right, and it turns out there's a simple identity that mu bar C left, mu C right is just the adjoint of the, it's just the equivalent to mu bar right, mu left. So you could have both present simultaneously. And if they are all there, or several of these are there, you can have, well, if they're all there or some are there, in general, you would have to diagonalize this to mass matrix, and we always have to diagonalize mass matrices, and there would be 2 mass eigenstates, which in general would be 2 Majorana mass eigenstates. There are several important limits. There's the pure Majorana, MD equals 0, with Majorana masses for the active and sterile. And of course, in that limit, one doesn't necessarily even have to introduce the sterile component. There is the pure Dirac, which is MC equals MS equals 0, and then although it would be written in a sort of funny non-conventional form, it is indeed does reproduce the Dirac case, and it's mu right goes to mu left, and mu C right to mu C left, so there would be a disturbed lepton number. And I'll just say in passing, I said that generally this matrix has 2 eigenvectors that are Majorana mass eigenstates. One can actually think, I don't want to develop this, but you can actually think of a Dirac neutrino or a Dirac fermion as 2 degenerate Majorana states. If T and MS were 0, then clearly that matrix would be like 0, 0, 1, 1, and the up cosine, the 2 eigenvalues are the same. So you can actually think of Dirac neutrino in some sense as 2 degenerate Majorana neutrinos with opposite sign for the mass. The sign of a fermion mass can always be made positive by redefining the phase of one of the components. Okay. However, I want to mention the seesaw limit. And I'll call it the type 1 seesaw. What I'm going to describe is often called the seesaw. Last time, I actually used the word seesaw in connection with that higher dimensional operator and said that anything that looks like that is a seesaw. Some people use the word that way. Some people use seesaw or type 1 seesaw for the specific model that implements that higher dimensional operator, which I will now describe. So this is the limit. One usually takes MC equals 0. So there's no X triplet, for example. And MD very much smaller than MS. So in other words, one has a mass matrix 0, MD, MD, MS, where this sterile Majorana mass term is very, very large. And MD is then going to be taken to be similar to the quark or charged lepton masses. Sometimes it's taken to be like the quark masses, sometimes like the charged lepton masses, but not, so it is generated by Higgs triplet, but without particularly small Yukawa. So large MS is due to the fact that if, for example, it's generated this way, this Higgs singlet may be associated with some very high-scale new physics, perhaps 10 to the 14 GeV or something like that. Well, in that limit, it's easy to diagonalize this matrix. The eigenvalues are M1 is equal to minus MD squared over MS, and M2 is approximately MS. These are not exact, but I mean, it's incredibly good approximation. And so you have one very heavy state, which is Majorana, and which is almost entirely associated with that sterile neutrino. And then you have one very light state called a seesaw, because again, it's a normal Dirac type mass times MD over MS, so it's inversely proportional to the big scale. Yes?
All the states later have generations.
Yeah. Let me just come to that in a moment. Here I'm just talking about one generation, and but I'll come to that one in a second. Okay, so first of all, so this is a way of getting a very small mass eigenvalue out of a very sort of normal Dirac without having to invoke a small power and having some underlying new physics that is very large. The light eigenvalues, I could have put zeros on here to indicate that these were the sort of weak eigenstates. The mass eigenstate associated with the light one is just mu L0, and then there's a correction. The first correction would be MD over MS times the sterile. So indeed, these eigenvectors are linear combinations of the act to the sterile, but in the limit I'm talking about, this is negligible. So this is a concrete implementation of that more general seesaw, and you can think of it diagrammatically